So yeah, hello. Thank you very much for coming. I hope you have a great PyData Paris. And yeah, I feel slightly overwhelmed after the keynote from Alenka. You know, Rock was mentioned several times. I was mentioned, so now I feel the pressure more than before. And we were mentioned on Arrow, not on Parquet. So why are we speaking about Parquet, Rock? So yeah, no, we will be talking a little bit about Parquet. We've been contributing a little bit to it also. So that's pretty much what we will be talking about. Rock is going to be doing the heavy lifting of the talk. I'll just give a brief introduction and history about the surroundings of Parquet and a little bit of the internal data structure, and then Rock will be talking more about it, the ecosystem, and what's coming to Parquet. What are the new things that the community is discussing? So who are we? Why are we talking about Parquet? So Rock, he's a physicist, starting doing some data science. Now it's part of the Arctos Alliance and G-Research, and he's an Apache Arrow PMC. He has contributed to Parquet, mainly to Parquet C++ and Parquet Rust, on encryption. He will talk a little bit about it. And I'm Raúl Cumplido. I work at QuantStack, one of the organizers of this conference. I'm also an Apache Arrow PMC and work mainly on PyArrow, Arrow C++, then continuous integration, general project management, and yeah, I'll be doing the next release of Arrow feature freeze on Monday. So yeah, I could have done it you know, during the conference, but that's challenging. So yeah, and I've also contributed to Parquet, mainly around statistics and some minor things there. So yeah, here's my dog, super cute, always on the pictures. So yeah, so Parquet as Arrow, Iceberg, etc., are community projects under the Apache Software Foundation, meaning they are governed by community under Apache, meaning that there's a PMC body, which is the project management committee, committers, contributors, etc. So if you're interested in contributing on any of those projects, you can join their mailing list, developer mailing list, and join, you know, their GitHubs, post issues, go there, find us, and yeah, ask questions. So all these projects usually have two parts. One is the format specification. So those projects are specifying how, for example, Parquet, the file has to be laid out. So it has a bunch of specifications. You can see the specification on this repository. And then there are a bunch of implementations of those specifications, same as with Arrow, Iceberg, etc. So yeah, so which are implementations of this format. Parquet is a de facto standard to store columnar data in files. Yeah, basically de facto because there's no someone telling you, yeah, you have to do it, right? But it's quite ubiquitous, it's used everywhere. Probably, I mean, no other format is as popular except for CSV, probably, because you still find a lot of things on CSV, even though, you know, technology has surpassed what CSV can offer. So yeah, Parquet is efficient in different accesses. For example, for storage, you can, you know, leverage compression, have a small footprint on disk. For read performance, for example, reading a column on Parquet is much more efficient than reading on CSV. Or on querying, you don't have to read the full file. You can read, you know, parts of the file, etc. Rock will explain a little bit more about that. Provides compression, different encoding schemes, and yeah, it's built for complex data. So a little bit brief history around the Parquet surroundings. Yeah. Things started with, you know, the famous MapReduce paper from Google, 2004, then 2005. We can see Vertica, which was the first database, commercial database using columnar storage, and then the Dremel paper, which inspired Parquet, Drill, and yeah, Apache Arrow. The Dremel paper, we will see a little bit more about it, on how it influenced Parquet with the definition and repetition labels, which is how you define the data in Parquet. And just a small brief thing about columnar format. Well, when we have our tabular data, we can store, you know, for transactional databases or how it's stored on CSV, on row format, so one row after each other. For transactions, this is pretty convenient because you have a new transaction, you append the row at the end. But when we want to do computation, where we want to do aggregations, we want to have better compression on our disk, etc., it's much better to have the data in columnar format, which would be the second one. Yeah. So some of the features on Parquet. It provides a rich data model. So Parquet has an explicit schema, which tells us specifically how our data is gonna be presented. So for example, here we have one example which tells you, which fields are required, which fields are optional, whether you have nested data, groups, repeated, etc. And yeah, that's how it's gonna be represented. And it's useful for random reads. So on Parquet, what I mean here is that you don't have to read everything. You can go and read specific columns, leveraging the use of statistics, indexes, and others. And you can use parallelized reading because, you can read several rows, pages, in parallel. So yeah, it provides optional columnar encryption. Rock will give more details about encryption later. And yeah, pages can be compressed and yeah, different encodings per column. So this is what a Parquet file looks like inside. So basically you have this magic number at the beginning. And then what we do is we split our table into different row groups. So basically a row group is like a slice of our table, we could say. And this row group has different columns, and these columns are separated into different pages. In these pages, we see these definition and repetition labels that I've been hinting around. Rob will show a little bit more later, and the actual values of our data. And at the end, we have our footer. Our footer contains a bunch of metadata, which tells us the length of the footer and then where each one of these rows is presented. It also contains some statistics like min values, max values, null count, etc. So you can leverage this. For example, if you want to read columns where the value is higher than X, you can skip certain columns just by using these statistics. So yeah, and yeah, here, so metadata is written last. You can use a single write, so it's written sequentially, and then all the metadata. And this is great for cloud storage, etc. So you can write. So you don't have to jump around the file to be writing. So you can just write in one pass. And that's me.
Thank you, Raúl. So yeah, let's go now further down into how data is stored. So first of all, the whole Parquet file will have a single schema. And the schema is inspired, the way the schema is done is inspired by the Dremel paper. Namely, it can be arbitrarily nested. And if you look at the schema up here to the top right, this is, you see the nesting. But you have to now realize that every leaf node in this graph, if you think of it as a graph or a tree, represents actual data that gets stored, like physical data that gets stored, while the under nodes, the ones from the root to the leaf, are not actually physical data. And both these records here, they conform to this schema. So the fields can be annotated as optional, required, or repeated. And further, they can be annotated with logical types. So Parquet only knows 8 of which one is deprecated, this 96-bit types. So to construct things like a timestamp, you have to add some logical annotation. So going further, so the leaves, as I said, of the schema are mapped to physical columns. So these two records here can be represented as these columns to the right. And now to explain the algorithm, and don't worry if this goes over your head, it's something that you need to know when you implement, and you should really come away only with an intuition of what's happening here. So Definition levels specify how many optional fields in the path for the column are defined. So, for instance, let's say code ENUS is stored here in the path to this field. So this is the code which is here. We have required. This is a repeated, which is optional, I think, and then we have a required. So the definition level is 2 in this case. A repetition level specify at what repeated field in the path the value has repeated. So this would be the first appearance of the ENUS, while the second code here is repeated at the second level. So the depth here is 2, and so the repetition level is 2. So basically, this gives you a lossless way of representing nestingness of values in the schema, and enables to write such nested things as columns. And that's the breakthrough here, the interesting part. And because we write data now as columns, this helps us with schema evolution further on. It helps us with null handling, compression efficiency, and single pass sequential writing. And it's more like Arrow in this way. Okay, so of course nothing is as simple as that. Values don't actually get written out like columns like this, but they get encoded before. Well, if they're plain encoded, which means that they're just written out as bits, then yes. But otherwise, we have options of other encodings. For instance, dictionary encodings, run length, delta byte array. So what you should take away from this is there's different encodings that will fit your data better or worse, and certain encodings don't support certain data types. So, for instance, if you're storing paths, like file paths, delta byte array is a good bet to go with. I'll give an example here of the run length dictionary. So let's say we have a list of values here, or rather a column of values. We first encode it with a dictionary, and we get encodings here, right? So this data equals these 2 columns. And then to encode the encoding further, we can do run length encoding, which basically means we store how long does a certain value repeat and from which offset. So let's say 0 repeats 4 times here at this index, right? So that would be your run length encodings. And then these, because usually this integers will be small, it's actually then commonly useful to also bit compress them or bit pack them. So we can say, okay, this integer, all the integers in this list can be don't actually need to be expressed with 8 bits, but we can actually express them with 2 bits. And so these values here are stored then in a buffer like so, right? So this is what actually gets written to disk, and we store a bunch of valuable space. So another way that we then further complicate things with columns is we can compress them before we write them. So Parquet uses external libraries to do that. What you should know here is that Snappy and Z standard are quite commonly available. So not, I don't think you mentioned, yeah. The Parquet has many implementations. Not all implementations will have all features available. So what you should probably think about is whether the compression you want to use is available in your implementation. So in that case, usually Z standard is the most common. So probably the one you should pick. Right, now going forward, when we actually want to write then a data page, it's a page is the indivisible unit that actually gets written into a file. So the compression, encoding, and encryption get applied to it. There can be multiple pages, page types interleaved in a column chunk. Well, this is for the next slide maybe. And a page will also contain a thrift encoded header with the repetition and the repetition and definition levels if required by the values. So repetition and definition levels are only included if there's actually nestedness going on, otherwise they can also be skipped. Right, so further, a page will live inside a column chunk, and a column chunk contains data pages for one column. If it's a dictionary encoded column, it will also contain its dictionary. So in the metadata, I believe, or not? No, it's actually a page that contains the dictionary. And then finally, column chunks get put together in a row group. So a row group, you can think of it as a logical horizontal partitioning of your data rows. So let's say you have a table, and if you cut it vertically, you get columns. If you slice it horizontally, you get row groups. So a row group will then be composed of column chunks, right? So kind of makes sense, I hope. Right. A row group will contain only one column chunk per column, and a file can contain one or more row groups. I suppose 0 is also possible for a file, but doesn't make much sense. I don't know. Yeah. Just the schema. Yeah, I think probably. I have to ask Antoine later. So metadata is written in a footer. So in the end of the file, we put the footer, and after the footer comes the second magic number that kind of terminates the file. It's put there because it enables us to do writing in a single pass. So we write like the column chunks and the pages. Well, let's say our source is some sort of a scanner that's throwing out rows, and we can then, batch a bunch of rows into a row group. And as we write the row group, we go per column and we write these row chunks. And then we take another batch of rows and we write another row group. And as we go, none of this data needs to stay in memory. We just write it to disk. What we do is aggregate metadata so that at the end of the write, we rewrite it underneath. So footer can also include an optional page index, which I'll go into later. And it also allows for another option, which is to put the footer in a separate file to data. So let's say you could have multiple files and then another file that just contains the footer, and that gives you kind of like a poor man's index to the other data. This works, but and it's popular with some people, but not. But it's kind of like you really need to go into optimization to end there. Further, columnar encryption. So columnar encryption was designed to give writers an option to encrypt either certain columns or the entire file. It's integrated into the Parquet standard, so there's metadata that's assumed to be there for it. So columns can be encrypted or can be left plain text. The encryption is symmetric, AES, GCM, or CTR with 128, 192, and 256-bit keys. Now, unfortunately, key management is left to the application, so you have to handle your keys. This turns out to be quite a technical challenge sometimes, and especially with crypto where you can't really afford to do any mistakes, so proceed with caution. When columns are encrypted, the encryption will provide tampering protection, so nobody can change the data on you, because you would always notice when you come to decrypt it and the key doesn't work suddenly. And it provides, of course, privacy. Nobody can read your data without your key. now the alternative to this approach to columnar encryption would be to encrypt the whole file as like a single blob of bits, but that will, take away the all the read optimizations that Parquet brings, because here data and metadata is encrypted, so like you can't access statistics, but you can still access page indices and such, so you can still parallelize reads, or you can do offset reads, so it still lets you do that. Yeah, so that's that. And further, let's go to page indexes. So the goal here is to allow lookups to exact pages that we want based on their row indices. We want to allow for page skipping based on statistics. So for instance, min and max values within a certain column. And we want to avoid scanning full columns if at all possible, because that will incur a lot of reading. And let's say we're reading from a data store from like S3. It would take a lot of time to read, and a lot of data would be pulled out or into the cloud. So we want to avoid these. So the structures that we have is a column index that stores, so this is in the footer, we provide a column index data structure that stores statistics per data page. And this allows us to filter on certain things. So let's say it stores a max of a column. And if you're looking for values that are greater than the max, then those pages can be omitted. And then we have another structure that's offset index that maps to the offset of where the page is from the ID of the row. And of course, effectiveness of this approach depends on your data. If your data is all nulls, this will work great. But if it's like if it has standard distribution, you will have to do a certain amount of work to use it. Certain amount of scanning. So further, another tool to help us speed up things is Bloom filters. So in case our data is non-numeric, we want to approximate that certain predicates, certain conditions are true for certain rows. So a Bloom filter is like will give us a probabilistic estimate whether a certain row will fit our filter, and based on that we can remove scans over some pages. Right. So further, and I'm not the most knowledgeable on this one, but Joris is. He's here somewhere, so you can ask him. GeoParquet effort. So recently, GeoArrow community or Geo community decided that they also want to use columnar data layouts for the benefits they offer. So GeoArrow. There was a GeoArrow effort that defined an in-memory layout for vector data, for geovector data, so points, lines, and polygons. That turned out to be quite useful and successful, so they proceeded on to make a guidance specification for Parquet as well, and that was implemented quite quickly with many downstream users. And so much so that Parquet ended up adopting it, and it's already in. I'm not sure which release, but for instance, you can go to QGIS 3.5 and read GeoParquet quite well today. Another extension that's happened recently was content-defined chunking. So this is, so if you imagine you have your data, you're chunking it into chunks, and your row groups will always have the same length. However, if you then go and update a row in this data set, because you have these static row group sizes, next time you chunk, all of them will have, all the chunks will change, right? So what you can do as an optimization, you can use a rolling hash function that will try to always hash in the same way, even if the data changes. So that makes the writer a little bit more complex. But because you always get the same, but it only needs to be the writer that changes. And then the writer can detect, can make these consistent chunks over writes. And if it detects that you've already written such a chunk before, it doesn't rewrite it again, but rather just references the old chunk that's the same, and you're golden. And last but not least, the variant type. This is a very recent effort. It's not completely landed, I think, but it allows to use binary, unstructured binary data in a column as if it was partially columnar. So basically, you write this binary data, and you have an option to shred out a part of it into a column, and this will be done by Parquet, and we'll kind of, for example, if this is like a JSON thing here, if you shred it, it will give you this event type thing will appear here as a column, and on the column you can do the usual columnar improvements, optimizations. So it will give you all that benefits. This is quite a deep topic, so definitely go check it out if you're interested in this. Okay. Oh yeah, I guess that's the last one. So yeah, limitations of Parquet. Just quickly, we have a lot of implementations and not all cover all features. That can be a problem sometimes. Metadata reading can be inefficient if you have very wide schemas. So be mindful of that. There's work ongoing, but it's not there yet. Encodings are not friendly to random reads within pages. So within a page, you can't really do random reads. You can do them over the entire data set. And yeah, okay, I won't cover the rest. If you're interested, there are some alternative data formats that you can look at. And if you have time, let's do questions. Thank you.
We have a bit of time for questions.
Thank you. I actually have two questions. One quite simple. It's like when I was first introduced to Parquet, they told me it's like a medium between row-based and column-based because it's like intertwined rows and columns. Is it because of the pages?
Yeah, it trades off some columnar benefits for compression. Yeah, so it's harder to do a random read. So a read at a random offset, it's harder to do, right? You need to decode some of it. You have to scan some of it. But it's still a pretty good trade-off, and it's really optimized for the industrial use cases. So yeah, kind of in between, yeah. But still closer to columnar. Second question.
Okay, got it, thank you. So I have a use case at work where I have a pretty much, how do you say, like a JSON kind of thing, like nested, right? Would you recommend me to actually store the entirety of the nesting thing? Or let's say if I know that my nesting is like a dictionary with kind of always the same 5 columns, to manually break it down and like facilitate the column search versus using the feature.
How big is your schema, and is it stable?
Yeah, it's let's say it's stable. Yeah.
Okay, so then I would advise to just try reading it directly into columns, and if you don't have certain values filled in, leave them as null.
Okay. Yeah, makes sense.
I would try that.
Yeah.
If the schema is bigger, then look at the variant type. I'm not sure if it's available yet.
Not in all implementations. So in some implementations it is, but not in all. So yeah, you can take a look. For example, on the Go implementation, you have the implementer there, so you can ask him. So yeah.
Yeah. Otherwise, you can also just store a string column and parse it later, but that doesn't give you much benefits. Yeah.
Yeah, I understand. And like the trade-off of wide versus not so wide, what is it like? If it's very wide, I should break it up? Or?
So if it's 10,000 columns, then you should start thinking about other approaches.
Okay.
Because at that point, the metadata gets so big, it gives you a significant amount of read work.
Okay, thank you.
Welcome.
One last question. Then you can continue to discuss at the coffee break in case.
Yes, we'll be here. Daniel.
Thanks for the talk. I was curious how, maybe you said this and I just missed it, but with the encryption, how does that work with like the metadata, the statistics? Because like, are those encrypted too, or you can't use them?
Yes, so it gets encrypted as well, yeah. So for the columns, you're encrypting the metadata is encrypted as well. You have an option to have plain text footers, and in that case, metadata doesn't get stored. So the data is encrypted, plain text footer is not encrypted, and so you're flying without statistics.
Great, so let's thank our speakers again.
Thank you.